So, so again the start of new lecture, and we will just review the last lecture. So, in the last lecture what we did was we looked at the thermodynamic point of view of ferroelectric phase transition. Now, this is essential because because ferroelectric phase transition is a phase transition where not only you have change in the properties, but also change in the structure or symmetry of the material. And depending upon the type of phase transition, you see a different kind of behavior in the way properties change. So, basically in the state of equilibrium, thermodynamic state of a ferroelectric material can be expanded in terms of, you can write a free energy expression, and that can be expanded in terms of parameters like electric field, polarization, stress and strain. So, assuming there are, for instance, stress and electric field can be treated as external variables, strain and polarization can be treated as internal variables. So, you can expand this free energy expression, and this we wrote as G was function of Px, Py, Pz, components of polarization, and then you have sigma x, sigma y, sigma z, sigma xx, sigma sorry sigma xy, sigma yz, and sigma zx, and temperature. So, you can of course write this in many parameters. So, in the context of ferroelectrics, we are writing this in terms of these parameters. Now, at a given temperature, or let us say not even at a given temperature, but for an unpolarized or unstrained crystal, you can expand this for a ferroelectric as half AP square plus 1 by 4 BP 4 plus 1 by 6 CP 6 and so on and so forth minus EP. So, this expression, which is a simplified expression, of course, we have removed parameters like, because in principle there could be parameters like electric magnetic field, etc. So, we have got rid of them simply because we are only considering unstrained unpolarized ferroelectric crystal. So, in such a case this equation works well, and so here we saw that A, B, C were the temperature dependent coefficients, and P of course is the polarization, E is the electric field. Now, at equilibrium you have to minimize the free energy has to be minimized with respect to P. So, basically del G by del P at constant temperature has to be equal to 0. Based on that we determine what is called a susceptibility. So, for a second order transition we worked out the susceptibility to come as chi was A inverse, which was nothing but P by E, and this is the classic equation that you got for normal material. So, this is the dependence of this is the susceptibility above the transition temperature in the paraelectric state or in the unpolarized state. When A changes its sign, so when A is less than 0, which means when T is less than Tc, then it becomes ferroelectric, and the free energy polarization plot start showing two minimas. So, here in this case you had only one minima, and this was the this was at P is equal to 0, and here you have minus PR or plus PR, and this is the 0 point, and these two are equidistant from 0 point. So, so this we looked at as a second order phase transition, and from this we also determined for the second order phase transition that A is less than 0, B is greater than 0, and C is greater than 0 at T less than Tc. So, when this was the situation, then of course, we looked at the derivative of del G by del P. So, del G by del P at constant temperature was equal to 0, and at just close to Tc, this P was equal to Ps. So, you make it APS plus BPS cube, and this gives rise to PS square is equal to minus AYB. So, here you get the magnitude of Ps, and of course, you can replace this A with T naught minus T or T minus T naught, depending upon how you write it. I think in the last time in our exercise we wrote this as, so we wrote A is equal to A naught into T minus T naught or T naught or Tc. And then from that you get an expression for P naught square, which is the Ps square saturation polarization near Tc, and then we got what we call as susceptibility near the transition below Tc as 1 over above Tc as 1 over A naught into T naught minus T. So, of course, you can see that near T naught it is going to go to very high values, or 1 over susceptibility is going to go to 0. So, which is what is depicted in this curve. And then we looked at the specific heat and so on and so forth. Now, since you know that we will just dwell a little bit on second order transition before we move to discuss the first order transition. You know, the ferroelectric for a ferroelectric crystal which shows second order transition, you can write this free energy expression as dg is equal to minus S Tt plus EdP. Now, of course, here I have not taken the pressure term because we have taken the pressure to be constant, and so if pressure term was there, you would get this Vdp term as well, and since dP is equal to 0, we can get rid of that, because you know that from the thermodynamic principle G is equal to H minus Ts. So, you have to expand both H and Ts in terms of all of the parameters. So, if dG was equal to this, then electric field can be related to del F by del P at constant temperature. So, this is fine, and since at temperature greater than Tc, since electric field is very small, almost tending to 0, let me just almost tending to 0, you can make certain approximations. So, in this region you can neglect all the terms in the right hand side of the equation. So, that gives you basically the susceptibility in the paraelectric state. Now, if you want to calculate the susceptibility at T is less than Tc, we have already calculated susceptibility in this case, let us say T naught. Let us maintain the convention. So, even in the previous slide it should be T naught, because Tc we have defined as something, as we will see it would be something else slightly different. All right. So, at T less than T naught, so you can write this del F by del P as is equal to E. If it was equal to 0, then this becomes AP plus BP cube. So, you can write this 1 over chi, let us say B, and this would mean susceptibility T less than T naught, and so this can be written as del E by del P, del E by del P, and if you again differentiate it, this becomes A plus 3 BP square. Now, you know that if E is very small, then Ps can be written as, so from this expression you can get, if E is very small, then Ps and P is equal to Ps in the vicinity of Tc, you can get so you can say T naught minus. So, this will become AP plus BP cube to be equal to 0, APS plus BPS cube to be equal to 0, and this would give rise to PS as minus of PS square as minus of A by B. and this is what we got earlier as well. Now, what you do is that you replace this in this above equation. So, 1 over chi b becomes, so expression was a plus 3b. So, a plus 3b multiplied by minus of a by b. So, b cancel each other and this becomes minus of 2a. So, 1 over chi b now becomes minus of 2, and what was a naught into t minus t naught, and here this is for t less than t naught. So, of course, it would be positive because t is less than t naught. So, minus minus will cancel each other, and since a naught is a positive quantity anyway, so this would remain positive. So, this is the magnitude of chi at temperatures less than t less than t naught. Now, we also looked at specific heat earlier. You can also do it in a different manner. You know that dg is equal to minus of s dt plus v dp. Just go back to previous slide. This should be g, not f. So, if dg was equal to minus s dt plus v dp, or sorry E dp in this case, because we are taking at constant pressure. So, here P is nothing but polarization. Okay. So, and F as and G as we know is equal to half of AP square plus 1 by 4 of BP 4 plus 1 by 6 of CP 6 minus EP. This was the expression for G, and you know that entropy is given as minus of del G by del T at constant pressure. So, constant pressure will mean this is your and this would be in that case S naught minus of half P square dA by dt. Okay. So, at constant polarization, not pressure. So, dG by dt at constant polarization. So, you only differentiate A, B and C. So, S naught minus, so you can write this basically as change in the free energy, change in the entropy, minus 1 by 4 P4 into dB by dt and so on and so forth. So, basically this would be S naught minus S, S minus S naught. You can take S naught on the other side. So, if I take this, so this becomes S minus S naught, which is delta S. So, to the first approximation, you can write this, if you ignore the higher order terms, this delta S can be written as minus of half P square dA by dt. Now, you know that for a second order transition, P is a function of temperature, but it is a continuous function. It drops continuously at Tc. P but the slope of P square has a discontinuity at T is equal to Tc. Now, this, since this has a discontinuity at T is equal to Tc, since A is equal to 0. So, as A is equal to 0 at T is equal to T naught, or the critical temperature or the transition temperature, there has to be a discontinuity in the delta S, and if there is a discontinuity in delta S, you will have a discontinuity in the specific heat as well, because as you know that specific, this delta S is also related to Cp, and this is, so delta you can write for a crystal as delta S to be equal to Cp ln T2 by T1 minus R ln P2 by P1. So, this is the expression which relates delta S to Cp. So, if there is a discontinuity in delta S at T is equal to T naught, there has to be a discontinuity in the Cp. So, second order transition is characterized by a discontinuity in the specific heat or entropy near at T is equal to Tc. So, this is another, but without any evolution of latent heat. So, there is no extra heat term which is coming into picture. So, so second order transition would basically mean P drops continuously till T naught. Discontinuity in specific heat at T is equal to T naught, and no evolution of latent heat. And this tells you about the nature of the transition. If there is no evolution of latent heat, which means when the material is going from one state to another, there is not massive reconstruction taking place. So the transition is more or less it's rather it's not that destructive in nature, you can say. It's not like liquid to solid transition where you have evolution or absorption of heat depending upon when you cool or heat. It's rather it's a transition where you have change in the specific heat, discontinuity in the specific heat at the transition, but no evolution of latent heat. So, in that sense it is not destructive transition. So, what we will do now is that we will now shift to, we will now look into other kind of transition which is called as first order transition. Now, this first order transition is as far as the plot of free energy versus this polarization is concerned. So, for an unpolarized crystal, if you plot G versus P, unpolarized crystal will show you a plot like this. So, showing you a root at P is equal to 0, but for a polarized crystal, so this is at T this would be at T greater than T naught, and there is another temperature which is called as T c. So, T is equal to T c, which is less than T naught. So, if you have the crystal in the state of where so this is at T less than T naught, but greater than T c. So, basically T c less than T naught. So, if temperature is between T c and T naught, a characteristic temperature, then the free energy of all these three states is equal to is equal. So, basically this is plus P r, this is minus P r, or minus P r plus P r to maintain the convention, and this is 0. And when you go to temperature less than T c, then of course it assumes same plot as of first order transition. So, this is temperature less than T c. So, it is this presence of a subsidiary minima. So, you see one more minima in addition to what you saw at less than T c in case of first or second order transition, that makes this transition interesting. And what happens here is at higher temperatures, of course, only A is negative, but at lower temperatures what happens is that A is negative, B is negative, and C is positive. So, for such a condition, when you have this behavior in A, B, C in such a manner, so sorry, here it would be A greater than 0, and below the T c it would be A less than 0, B less than 0, and C greater than 0, and somewhere in between it would be so A would be equal to 0 at, so this you can say between T c and T naught. Now, here what we will do is that we will now again analyze this picture quantitatively. So, this is a situation for a first order transition. Note the difference is difference with the second order transition, that not only you have change in the A sign of A as you had in the previous case, here the sign of B is different. So, B is negative as well. in the case of first order transition. So, at now we can do a bit of quantitative treatment. So, at A is equal to 0, we obtain P is equal to 0 gives you a minima, in G, and two other at so this is what it is. So, you have one minima here and then another minima here. So, this is G so A is equal to 0, and which means that polarization has a discontinuity at, and this also means that polarization this kind of transition also means that polarization has a discontinuity at t is equal to T naught, and basically what it means is that when you plot the polarization versus temperature plot, in the second order case, in the first order case, polarization goes like this and then suddenly drops to 0. So, this is a discontinuous transition, and susceptibility again even in this case and susceptibility also follows a similar trend. It also shows a discontinuity at at this temperature. So, basically what will happen is the susceptibility will show a transition like this. So, there is this discontinuity here. So, if you just extend it here, so if this is not T naught, this becomes T c. Okay. So, this is your 1 over chi. So, in addition to so here not only you have entropy which is discontinuous. So, as you can see from the case, because since you have a discontinuity at T is equal to T c, not only you have discontinuity in the entropy at T is equal to T c, you also have evolution of latent heat. So, for the first order transition, again the some of the features are, so and you also have evolution of latent heat, and this is what makes it different from the second order transition. So, these are two important features of a first order transition. So, let us do now the quantitative analysis. So, let us say at E is equal to 0 under equilibrium, so at E is equal to 0 under equilibrium, we have del G by del P at constant temperature equal to 0. This is what is the standard expression. So, this gives rise to, in the vicinity of T is equal to T naught. So, I am writing T is equal to T c. So, let us just make a distinction here. Since we have said all of this, let us just see first order transition. So, this is T naught, this would be at T is equal to T c less than T naught, and this would be between less than T c. So, in the final slide this should be T naught. So, in the vicinity of T naught, let us take polarization as, and P is equal to P s. In the vicinity of transition, we can write we can take the same Frege expression that we took earlier, and this will give rise to P s into A plus B Ps square plus C Ps 4 and so on and so forth equal to 0. Now, at T is equal to T naught, this quantity Ps at Tc. So, Ps at Tc should satisfy the equation that we wrote in the previous slide, as well as the condition. So, Ps should satisfy not only the previous equation in the previous slide, but also should satisfy following condition. And what is that condition? That condition is that G at Tc, G at T naught is equal to G naught at any temperature. If this is the case, then since we know that G is equal to half of A Ps square plus 1 by 4 B Ps 4 plus 1 by 6 C Ps 6 and so on and so forth, we can write G at Tc. So, basically before we write this, basically G at T naught. So, basically what it means is that free energy at transition temperature T naught is equal to the equilibrium free energy, and this is basically equal to, and this is this should be equal to 0. So, this becomes so G of Tc is half of A into Ps Tc square plus 1 by 4 B Ps Tc square to the power 4 and so on and so forth, and this of course is, and this free energy at Tc is equal to 0. So, from these equations, so the first equation, that Ps multiplied by A plus B Ps square plus C Ps 4 and so on and so forth is equal to 0, and then the other equation that you get is half of A Ps square plus half of 1 by 4 of B Ps 4 plus 1 by 6 of C Ps 6 is equal to 0. From these equations you can derive that Ps square at T naught to be equal to minus 3 by 4 of B by C, and A comes out to be at 3 by 16 into B square by C, and Ps 4 Tc or T naught comes out as A divided by 3 of A divided by C. Now, since you know that since for this kind of transition B is less than 0, since B is less than 0 and we know that Ps at T naught is discontinuous, so basically if you look at the expression here, since you know that Ps square at T naught is equal to minus 3 by 4 B divided by C, and since we know that B is negative, this makes Ps discontinuous at and you know that A is also negative at transition, near the transition. So, now consider, so we will consider two regimes again, one above the transition and one below the transition. So, first consider the case of chi above and above T naught. So, above T naught we know that A is greater than 0. If A is greater than 0, then 1 over chi A is equal to A. This is simple expression. So, again it is in paraelectric state, and chi A as you know is given as the Curie-Weiss law, and this chi A becomes equal to a constant C divided by T minus theta, and since you know, and hence as a result A becomes equal to T minus theta divided by C. Okay. So, the theta is somewhat smaller than theta is smaller than T c sorry T naught, and this is called as T c. So, T c is smaller than T naught. Similarly, T less than T naught, you can write del G by del P, which is equal to E. This becomes APS plus BPS cube plus CPS 5 and so on and so forth. Since this is equal to 0, basically this was equal to 0, and so 1 over chi B, which is the susceptibility in the in the low temperature regime, this is equal to del E by del P, and this can be written as A plus 3B P 3B PS square plus 5C PS to the power 4 and so on and so forth. So, this 1 over chi B from the expression of PS, they can be written as A plus 3B into minus 3 by 4 of B by C plus 5 into C into 3 into A by C, and if you just do the math here simple, you get out 4A. So, basically at lower temperatures chi B is nothing but 1 over 4A, and at T is equal to T naught, as you know that A is equal to T naught minus T c divided by C, since theta is nothing but T c. So, 1 over chi B becomes 4 over T naught minus T c divided by C, and this is for T is equal to T naught. Okay. So, this is the expression that you get for the first order transition in the ferroelectric crystals. So, so basically the characteristics of first order transitions are that first order transition shows a discontinuity in polarization near the transition. It does show a discontinuity in entropy near the transition, but that is now assisted with evolution of latent heat, unlike what you see in the case of second order transition. So, it is just like in some sense melting, where you see evolution of latent heat. In the first order transition you see evolution of latent heat. So, this is the crucial difference between first and second order transition. So, if you draw both of them together now, if you draw second order and then you draw first order. So, here I am going to draw polarization versus temperature. So, polarization drops. So, this is your T naught, and susceptibility goes as so this is your 1 over chi, and if you draw the same plot for first order, for the first order the polarization goes and then it drops suddenly. So, that is your T naught, and then you have susceptibility which goes as and this is your 1 over chi, and the intercept here is called as T c. So, this is your first order transition. So, here basically no evolution of latent heat, and here you have evolution of latent heat. So, basically what you have is a discontinuity in the order parameter in the first order transition. In the second order, you do not have a discontinuity in the order parameter. So, and the meaning of the second order transition having two transition temperatures, one as T c, one as T naught, is because material, since we are saying that when you reach T naught, below T naught, you have between T c you have 3 minimas. Now, this has effect in terms of heating and cooling. So, what happens is that when you heat the when you cool the material from higher temperatures, then sample will remain in paraelectric state until you reach T c. On the other hand, when you heat it, it will convert to higher temperature state at T naught. So, as a result, there is a sort of hysteresis, and between T naught, between T c and T naught, material does not sort of remember its states and happen to show three minimas between these regions, and it depends upon whether you cool the material or whether you heat the material. So, it quite a lot depends upon thermal cyclic. So, this is basically essentially about first and second order transition ferroelectrics, and basically what it shows is that most of the ferroelectrics show first order transition. So, your materials like barium titanate, etc., they all show first order transition, and the second order transition is shown by materials like Rochelle salt, and KH2PO4, all these kind of materials show second order transition, whereas in most materials that we come across on daily basis show first order transition. So, first order transition, second order transition basically is a thermodynamic effect. If you want to go into details of it, you can again go into details of this I would prefer, if you want to understand, then go to this lines and glass, principles of ferroelectricity. And you can also go through Jonah and Chiran, and it is ferroelectric crystals. All right. So, so this is about the ferroelectric transitions in the materials. So, so we'll finish the so we have finished what is we have looked at ferroelectric materials so far. So, you have ferroelectrics, and these ferroelectrics have qualities as have characteristics like they are non-centrosymmetric, they are polar, and this polarization has two states, plus PS and minus PS, depending upon how you switch it. So, this is switchable as you change the polarity of electric field. So, this is the difference, and not only these three characteristics, it also undergoes a phase transition. So, this phase transition is from basically when you heat it. So, it is from a non-centrosymmetric phase to a centrosymmetric phase typically, or you can say it goes from lower symmetry to higher symmetry as you heat the material, and this, which means that it has a transition temperature, and this transition temperature is very precise in case of second order transition. So, in case of second order transition, you have a transition at T naught, and this T naught defines the transition temperature, and in case of first order transition, you have a transition at between T c and T naught, and it depends whether you cool it or whether you heat it, and The difference between these two transitions is that in the second order transition the polarization drops continuously up to the transition. In the first order the polarization drops abruptly at the transition. So, there is a discontinuity in the polarization which is called as order parameter for the first order transition, and it drops suddenly at the transition temperature, and this is also shown in the susceptibility of the first order transition, which shows the discontinuity. Another difference is in the second order transition you have discontinuity in the specific heat near the transition, but there is no evolution of latent heat. In case of first order you have discontinuity in the specific heat, but you also have evolution of latent heat. So, it is like liquid to solid transition in some sense, the first order transition in ferroelectrics. So, moving now away from the phase transitions, now what we need to look at how the ferroelectric materials switch. So, we know that the ferroelectric material, when you draw the hysteresis of ferroelectric, when you pole a ferroelectric material and you make a plot of polarization versus electric field, and this shows a curve like this. So, this is your plus PR, this is your minus PR, this is your plus PS, this is your minus PS, and this is your plus EC, this is your minus EC. Now, a ferroelectric material typically, now the question is why does it happen? Okay, why does it happen and how does it happen? So, when you start with a material which is virgin material, which is as prepared material, then typically in ferroelectric materials for a polycrystal you start at 0 polarization. Now, as you start from 0 polarization, which means what it means is that net polarization of the material is 0, although locally it still is polar, and that is for the reasons that I will show you in a while. And then it starts increasing. So, it goes like this, and then it goes like that, and once all the dipoles align in the direction of applied field, it gets back to non-zero state, and this process keeps happening. So, now what happens is basically in ferroelectric material you have anyway polarization, but these dipoles, as we said earlier, they are aligned in one direction. When they are aligned in one direction, and this alignment, when it extends over a region of the crystal, then this region which has a uniform alignment of dipoles is called as a domain. But the moment you form a domain, you have these ends of the, so if this is the P vector, then you have charge buildup on the faces of this domain, and this charge buildup starts increasing the electrostatic energy. So, now this, if this electrostatic energy goes up, then the depolarizing field becomes high. So, the counter field which wants to turn this other way around, that increases. So, the question now is what is the extent of this region? The extent of that region is governed by what is the depolarizing field. So, it is the competition between the energy which aligns all the dipoles in one direction and the depolarizing energy which defines the extent of this alignment. So, these regions of uniform polarization, so domains essentially are regions of uniform polarization, and typically what you see in the ferroelectric materials is you have these domains which are separated by, so you have one region. Now, monodomain state is not favorable for regions for reasons that we will see in a while. It is because of energetics, because the energy of the system does not allow it to retain the monodomain state. So, you have one domain. So, this is domain 1, in which alignment of dipoles is in one direction. You have another domain which is domain 2, and in which the alignment of dipoles is in another direction, and they are separated by a boundary which is called as domain wall. And this domain wall is not a grain boundary, because here you are not changing the crystal orientation, all you are changing is the domain or the polar vector. And how it happens is, so basically So, this domain wall first of all not a grain boundary, and what it also means is that domain is not a grain. So, grain and domain are two different terms. It is a different matter that one grain can be one domain, but domain and grain conceptually are extremely different. So, basically there are variety of domains, there are domains in various directions. So, for a polycrystal you have situation like this. So, this is your, let us say, a polycrystalline material. Now, these are grains. So, this is your grain boundary and this is your grain. Let us say this grain is big enough. Okay. So, you may have regions in this. Now, I am going to use different color. So, you may have these different regions of different domains. So, let us say orientation of this domain is this one. This is as prepared material. Orientation of this domain is that. This is this. This is that, this is this, this is that, this is that, and so on and so forth. So, the orientation of domain walls, orientation of polarization in the adjacent domains is restricted by the structure of the material, although here it is looking much more random, it is not that random. So, I will just come to that in a while. So, and so on and so forth. So, for a virgin material, in a polycrystalline material which is as prepared, all the domains are randomly distributed. So, even though the material microscopically is polar, the net polarization is equal to 0 when it is not poled. Now, when you start applying this electric field to this material, when you start applying electric field, so what happens is that now you have, so you have grain boundaries like this. Okay. And if you go to previous slide itself, so when you, so this is when E is equal to 0. Now, what happens when E becomes greater than 0? When E becomes greater than 0, then all these domains which are unfavorably oriented, they start. So, basically the in this case the ferroelectric, the domain creation or the domain movement in the ferroelectric materials is slightly different. So, what happens is that basically new domains form which are aligned in the direction of applied field. So, you start forming new regions, new domains which are aligned in the direction of applied field, and these domains grow as the field strength is increased at the expense of all these unfavorably oriented domains. So, all the basically old domains are consumed and new domains form which are conducive to the direction of applied field. And when the field is maximum and when all the domains, when the alignment of dipoles in all the domains is in the direction of applied field, that is where you have saturation. So, when E is very large, then saturation is achieved, which means you have achieved a monodomain state. But this monodomain state is not favorable. So, when you bring the field back to E is equal to 0, then all the domains get back to the same configuration, which means giving rise to a 0 polarization state. So, basically you have domains, you have domain walls. Domain walls are boundaries which separate the domains, and these domains are formed due to balance of energies. And as I will show you the analysis, these energies typically are your depolarizing energy due to depolarizing field and domain wall energy. So, what basically means that when you have a monodomain state, polarization is very high, but at the same time, since you build up the charge at the end of dipoles, the depolarizing field becomes large. When the depolarizing field becomes large, it wants to turn the polarization in the other direction. But when you turn the polarization in other direction in some parts of the crystal, you create these boundaries, and these boundaries are domain walls, and these boundaries or domain walls are nothing but surfaces, and surfaces require energy. So, it is a competition between these two energies which determine what is the domain size and domain configuration going to be. So, for instance, in a material like barium titanate, lead titanate, so you have a cubic material, you start with a cubic state of the material from high temperature. So, this is high temperature cubic state. So, when you cool it, cool below Tc, then what happens is that the material transforms into tetragonal state. So, this is now tetragonal. So, this was here it was AA. So, here it becomes A and C. So, AT and CT, here it was AC and AC. Okay. So, here what happens is that when it becomes tetragonal, it develops a polarization in this direction. So, you have buildup of charges on the faces of the crystal. Correspondingly, you have a depolarizing field which is called as ED. Now, this state being not, so this is a monodomain state, but this state is unstable. So, what you get instead is you have polarization in this direction, you have polarization in this direction. So, here, so the surface charge density goes down. As a result, you can see that the depolarizing field has disappeared, and these kind of domain boundaries, this wall is called as domain wall. So, this was single domain, unstable, and this state is basically multi domain which is a stable configuration. And depending upon the type of the crystal structure, you can have variety of domain walls. So, for instance, for a tetragonal material, domain walls are of 90-degree domain walls and 180-degree domain walls. What essentially it means is that you can have domain walls like this. So, P, so this is your 180-degree domain wall, and 90-degree domain wall would mean you have, for instance, a material like this. So, P in one direction and P in another direction. So, this is your 90-degree wall. And for similarly for materials like rhombohedral structure, you can have 71-degree domain wall, 109-degree domain wall and 180-degree domain wall. So, depending upon the crystal structure, the configuration of domain walls will change. So, in the next class, we will finish the lecture here. In the next class, what we will see is that we will look at the little bit analytical treatment of the domain wall, some pictures, how the domains look like, and how the configuration of atoms at the domain wall boundary looks like, so that you do not get confused with the grain boundary. It is slightly different from the, it is very different from the grain boundary. There is no change in the orientation of the crystal, or crystal orientation remains same, it is just the polar vector changes in one to another direction. So, we will finish this lecture here. So, in this we finished the phase transition, we looked at the first order phase transition in detail. We also looked at the remaining part of second order phase transition, and the crucial difference you must remember, in the first order transition the order parameter drops discontinuously near the Tc, whereas in the second order transition order parameter varies continuously until the Tc. And then we started what is called as domain wall, domains and domain walls, and these domains are stable features inside the material simply because monodomain state or alignment of polarization dipoles across the whole volume of the material is not a stable state. So, we will have a little bit more discussion in the next lecture. Thank you.